Hello students, today I'll be explaining the notes on advanced probability. So for the warm-up, if you haven't already tried it on your own, please pause the video and try it before watching. Okay, so it says from the whole numbers 1 through 7, Adam and Bill each select a number. So they do have the option of selecting the same number, and it says to illustrate the sample space on a two-dimensional grid. And it says to circle the outcomes in the event that Adam's and Bill's numbers are the same. So really we should probably label one of these Adam's choices and the other one Bill's choices, and then they each have the choices 1 through 7, so you'll list them both horizontally and vertically. And then you're going to circle the events where they chose the same number. So here's where they both chose 1, 2, they both chose 3, etc. All right. The addition law of probability. So we're going to consider compound events where there's more than one event in our sample space. And there are two reasons why this could be. Either because the experiment has more than one process, or because we're interested in more than one property of the outcome. And we'll see examples of both of those. Suppose there are two events, A and B. Following set notation, the event that both A or B occur is written like this. And you read that as the A intersection B. The event that A or B or both A and B occur is written this way, and that's read as A union B. So the addition law of probability is that if you have two different events, A and B, so here's A and B, perhaps they would mean A would be the probability that you like chocolate, and B would be the probability that you like potato chips. You would add the two probabilities together and subtract the probability that they both happen. And that kind of goes against your intuition because it says right here, it's the probability that A happens, or B happens, or both, right here. So why are we subtracting the probability of both? Let's look at an example to see if we can see that. Think here. Okay, so here we have 100 students. You can see there are 100 students by adding up all the numbers, 10, 30, 40, and 20. And these 100 students, you can see students who are in a physics class. You can see students who are in a math class. And here in the middle, these students are in both physics and math. So if you wanted to find the probability that a randomly chosen student was in math, you would consider both these and these students. That would be 70 students out of 100. So the probability that a randomly chosen student is in a math class would be 0.7. The probability that a randomly chosen student is in a physics class, you would add these two together, 60 out of 100, which is 0.6. But if I wanted to find the probability that a student was in math or physics or both, I could not just add up 70 and 60 because that gives me 130 out of 100. That doesn't make any sense. And the reason is because if we add the probability or the number of students that are taking math plus the number of students who are taking physics, you notice that we double counted this number in the middle. And that's why we subtract it, because we added it once, then we added it twice, and we have to get rid of one of those because those 40 students, they don't exist two times. That's why we subtract. All right, but sometimes we're going to have mutually exclusive events when the probability that they both happen is 0. So that could look like this one here. So it could look like this, like say the probability that I'm blanking from it. Probability that your coin lands on heads and the probability that your coin lands on tails, right? So maybe like 50 times it landed on heads and 49 times it landed on tails, but it's never going to land on both heads and tails, so there's no overlap. Sometimes it would look like this, and then sometimes it would look like this, but they would just have a 0 in the middle to explain that you're never going to have both things happening at once. So, when things are mutually exclusive, then the addition law becomes this one right here. The probability of A union B is just probability of A plus the probability of B, because the probability of them both happening is 0. So subtracting 0 doesn't change anything. So you get this simpler rule. Okay, let's look at this example. If the probability of A is 0.6, and the probability of A union B is 0.7, and the probability of A intersection B is 0.3, find B. And we can do this by using the addition law. And we know that it's going to be this one because the intersection's not 0. If the intersection were 0, then that would be mutually exclusive, and we would use the simpler rule. So copying this rule down right here, we simply substitute into it. And substituting in 0.7, 0.6, and 0.3, we can solve to find the probability of B is 0.4. Okay. Actually, why don't you pause and try the next section? Alright, you should have already paused and given it a try. Let's see how you did. 30 students were given a history test. 7 students scored an A, 11 students scored a B. A student is randomly selected, and let A be the event the student scored an A and B be the event that the student scored a B. Are A and B mutually exclusive? Well, yes, because you're going to earn one grade, which will be an A or a B or some other grade, but never more than one. So find the probability of A. So we said there are 30 students right here, and 7 of them scored an A, so the probability of A is 7 over 30. The probability of B, 11 students scored a B out of 30, so 11 over 30. The probability that they both happen is 0 because you can't get both grades. And so since they are mutually exclusive, you can use the simpler version of the addition rule where you just add these two probabilities together. The probability that you get an A or B is 18 out of 30, which you could probably simplify. Let's see, dividing by 6, we would get 3/5. Alright, similarly, two events are independent if the occurrence of each event doesn't affect the occurrence of the other. And if they're independent, the probability that both events happen is going to be the product of their individual probabilities. So probability of A times probability of B. And if you had more events, like A, B, and C, you just continue to multiply their probabilities if you want to find the probability that all those things happen. So number 1, a coin is tossed, a die is rolled simultaneously. Determine the probability of getting a head and a 3 without using a grid. So we know the probability of a head is 1/2, and the probability of the die landing on 3 is 1/6. And so to find the probability of them both happening, we just multiply those probabilities together to get 1/12. Alright, next one's about Carl's car. His car will only start 80% of the time, and his motorbike will only start 60% of the time. And those are independent of each other, so obviously one doesn't rely on the other. Draw a tree diagram to illustrate this situation. So you could have started with a motorbike, but we started with a car, and C is going to be the probability the car starts, and not C is the probability that the car doesn't start. So if there's an 80% chance it starts, then there's a 20% chance it doesn't start, and that's where we get these numbers from. Same thing with the motorcycle. 60% chance the motorcycle starts, which means 40% chance it doesn't start. Using the tree diagram, determine the chance that on the next attempt they both will start. So you're going to multiply those two probabilities together. The probability of C times the probability of M, and there's a 48% chance, which is 0.48, that they'll both start on the next attempt. Probability that the car will start but not the motorbike, and so we have to go to car and then not motorbike and multiply those two probabilities together. 0.8 times 0.4. 0.8 times 0.4. And that's where we get the 0.32 probability. Alright, and then number 3. Liam rolls a 6 sided die twice, determine the probability that exactly 1 4 is rolled. So when we roll the die, we can either get a 4 or not get a 4. And the probability of a 4 is 1/6, and the probability of not 4 is 5/6. So this is our first roll, and then after our first roll, we roll again. So exactly 1 4 could be 4 and not 4, or it could be not 4 and 4. So this one is 1/6 times 5/6, and this one is 5/6 times 1/6. Both of those give us 5/36, which add to 10/36 and simplify to 5/18. So let's talk about dependent events. This is when one event happening does change the probability of another one happening. So here's an example. Suppose a hat contains 5 red and 3 blue tickets. One ticket is randomly chosen and its color is noted and put back aside, so it's not put back in the hat. And then a second ticket is randomly chosen. What's the chance that it is red? So if the first ticket is red, then the probability that the second is red is 4 out of 7, because you started with 5 red, you chose a red, and you took it out. And so there are only 4 red left and only 7 tickets altogether. But if the first ticket was blue, the probability that the second is red is going to be 5 out of 7, because there's still 5 red tickets, but since you took a blue one out, there's only 2 blue, and that's going to add up to 7 tickets altogether. So the probability of the second ticket being red depends on the color the first ticket was, and we have dependent events. 2 or more events are dependent if the occurrence of one event does affect the occurrence of the other. Events are dependent if they are not independent. If A and B are dependent events, then the probability of A and B happening is the probability of A happening times the probability that B happens given that A has occurred. So you have to figure out this new probability. In general, when an experiment involves sampling without replacement, then we have dependent events because you take something out. And if it has sampling with replacement, when you put it back in, it's just like every single time you do the experiment, it's kind of the same experiment. Not all scenarios we study will involve sampling, however, they may still involve dependent events. For example, the event Pahal walks to school today is dependent on the event it will rain today, because one probability will change the other one. Alright, number 4. A box contains 4 red and 2 yellow tickets. 2 tickets are randomly selected from the box one by one without replacement. Find the probability that, and notice it says that it's dependent because it says without replacement. So the probability that you get red and then red. So the first red, 4 reds out of 6 tickets altogether is 4/6. And then if you take a red out, and the next one is red also. So if we take a red out, now we only have 3 red, and 3 plus 2 would make 5 tickets altogether. So we multiply those 2 probabilities together. Alright, why don't you pause the video and see if you can figure out the next one before you go over it. So the probability of red and yellow, first one red is still 4/6. We take out a red and we still have 2 yellow. However, we took out a red, so we have 2 plus 3, so we only have 5 tickets remaining. And then we'll simplify your final answer to 4/15. A hat contains 20 numbers, numbered 1, 2, 3, 4, 5, all the way up to 20. If 3 tickets are drawn from the hat without replacement, determine the probability that they are all prime numbers. So first we have to figure out what are the prime numbers, and here they are. So we have, there they go, 1, 2, 3, 4, 5, 6, 7, 8 prime numbers. Now each time we take one of these prime numbers out, it is gone, so the second time we'll have 7, and then we'll have 6. So why don't you pause the video and try to figure out the probability that all three are prime numbers. Alright, so what you should have done, probability of prime and prime and prime. First one is 8 out of 20. We take a ticket out, there are only 7 left out of 19, and then we take a ticket out and there are only 6 left out of 18. And we get a fraction, which you can convert to a decimal to 3 sig figs. Two boxes each contain 6 petunia plants. Box A contains 2 plants with purple flowers and 4 plants with white flowers. Box B contains 5 plants with purple flowers and 1 plant with white flowers. A box is selected by tossing a coin, and 1 plant is removed at random from it. So let's see what that would look like. That's box A, and then box B. Find the probability that the plant was taken from box A and has white flowers. So, the probability of getting box A is 1/2, and then the probability of getting white from box A is 4/6, and so we'll multiply those and simplify your answer to 1/3. The probability of purple flowers is going to be the sum of the probability of A in purple and the probability of B in purple. So A in purple was 1/2, B times 2/6, and then B in purple was 1/2 times 5/6, and that's going to give us 7/12. Bag with 10 balls, 6 of them are black, 4 of them are white, and 3 balls are drawn without replacement. Find the probability that 1 black ball is drawn. So the black ball could be the first one, or the second one, or the third one. So we're going to find all 3 probabilities and add them up. So remember, without replacement means that your denominator goes down 1 each time. And in the first one, we had 6 black balls, and then we took 1 out, and the white, next one will be white, which is 4, and then white again, and we took a white one out, so now we only have 3. The next one, first we had 4 out of 10 for white, and we took a ball out, so we only had 9 left, but we still had 6 black balls, so 6 out of 9 is going to be the next one. And then remember, for this one to be white, we had already taken out that first white ball, so there's only 3 left and only 8 balls altogether. And then similarly, you can see the probability of white, white, blue. Each of these will simplify to 1/10, and so there's a 3/10 probability that exactly 1 black ball is drawn. All right, and now we are on conditional probability. So we have a Venn diagram of students who study Italian and French. And a student is randomly selected from the class, and it's found that the student studies French. We can determine the probability that this student also studies Italian. And we call this conditional probability because it's the probability of I occurring on the condition that F has already occurred. So we have the probability of I given F. And that's going to be, what you want to consider is that we already know the student speaks French. So we're not considering all 30 students anymore. We're just considering these 15 students that speak French. So out of these 15 students, the probability that they also speak Italian, we can't consider these because they don't speak French, just these. So 8 students will, out of those 15 will also speak Italian. So you can also do this with a formula. We use this notation to represent the probability that A happens given that B happens. And the formula is the number in the intersection, which is 8, over the number of the given event, and that was 15. So you can use the formula or you can reason it out. And we can also develop the conditional probability formula with this method. And notice what we started with was the number in the intersection over the number in B. And here we have the probability of the intersection over the probability of B. So both can be used. Here's a more complicated question. In a town, 25% of the residents own a cat and 55% own a dog, and 30% don't own either. So we know 30% is down here. What we don't know is how much is in this overlap here. So one way to do it is if we know this whole circle is 25 and we call the overlap x, then what's left over here on the left is 0.25 minus x. And what's left over here is 0.55 minus x. And then if we know that all the probabilities have to add up to 100%, which is 1, you can add all of these expressions up and you can solve for x. Find the probability that a randomly selected resident owns a cat given that they own a dog. So let's go back to our Venn diagram right here. Here it is. So we're going to use the formula, probability of cat and dog, that's that 0.1 in the middle, divided by the probability of dog. And that's going to give us 0.182. Does not own dog given that they own a cat. So again, we're using the formula, probability that they don't own a dog, but they own a cat is right here. So these are people who own a cat and not a dog, 0.15, over the probability that they own a cat. And we have to add the 0.15 and the 0.1 to get 0.25. Finally, you divide it and get 0.6. Alright, I think this is our last one. The top shelf in a cupboard contains 3 cans of pumpkin soup, 2 cans of chicken soup. The bottom shelf contains 4 cans of pumpkin soup and 1 can of chicken soup. Lucas is twice as likely to take a can from the bottom shelf as he is from the top shelf. So we need 2 fractions that are going to add up to 1, 100%, which is 1, where 1 is twice the other. And so those 2 fractions would be 1/3 and 2/3. Now once we know if he's going to the top shelf or the bottom shelf, we do know the probability that he's going to choose pumpkin soup or chicken soup, because the top shelf is 3 pumpkin and 2 chicken, so 3/5 and 2/5. The bottom shelf is 4 pumpkin and 1 chicken, so that's 4/5 and 1/5. Suppose Lucas takes 1 can of soup without looking at the label. Find the probability that it's chicken. So we're going to add together the probability that it's from the top shelf and chicken and the probability it's from the bottom shelf and chicken. And so what we're going to do is multiply across. So top and chicken would be 1/3 times 2/5. And then bottom and chicken would be 2/3 times 1/5. And then adding those 2 answers together, we get 4/15. The next one says, was taken from the top shelf given that it's chicken. So we have top and chicken over the probability of chicken. We already know the probability of chicken is 4/15, we got that right here. So to find the probability of top and chicken, it's going to be 1/3 times 2/5. And then simplifying our answer, we get a 1/2 chance. Probability that's from the top shelf given that it's chicken, 1/2.